Saxon Advanced Mathematics, Lesson 10. We have 3 topics to review in this lesson. They're all lovely algebra. They're all useful and valid, but it's a lot. So let's dive in. The first thing we're going to talk about is equation of a line. This is one of the hot topics. When people think about algebra, this is one of the biggies that they imagine. And so without further ado, I'm just going to jump into a problem and we'll review as we go. Find the slope-intercept form of the line that passes through the points, and I'll write it down, -3, 2, and 4, -3. Okay. When you hear this slope-intercept form of the equation of a line, this is what I want to jump into your head. Y equals mx plus b, yay! We know that these 2 letters stand for numbers that will be fixed within an equation. We'll always have the x and we'll always have the y, but we'll have specific numbers in each particular equation for the m and the b. Remember that the B represents the Y-intercept. This number shows where our line crosses the y-axis, and this is what we graph first. M is the slope. It is a fraction. If it's not a fraction, we make it one by putting it over a 1, and it tells us where to go after the y-intercept. We'll review that as we actually graph a little bit later on. But there are 2 ways to think of the slope. If it's positive, the numerator is the rise. It's how many steps you go up from the y-intercept. And then the denominator is the run. It's how far you move to the right to get that second point, right? We plot this first, then we go up and over if it's positive. If it's a negative slope, I call that the sink. We go down first, and then the run is still to the right. So the slope can be positive or negative. Positive slopes go up, negative slopes go down, and here's my favorite diagram in the whole wide world of John Saxon. Look, these are positive slopes going up the graph, and look, can you see? Can you see that amazing little woman in her car driving along? She's going uphill. Negative slopes are, woo, they're the downhill side. And there she is careening down the negative slopes in her car. I think that's about the finest thing that life can offer, is a little lady driving her car up and down positive and negative slopes. I love her. I will talk about her as we're actually graphing. I knocked my studio sideways in all my excitement, my gosh. Okay, so what do we do about this? We don't have a slope, we don't have a y-intercept, we just have these points. But what the other thing we have, if we don't have our slope, is we have something called slope formula. And it allows us to take 2 pairs of points, stir them up in this lovely soup, and it'll spit out our actual slope. This is called slope formula. Make sure these are in your book. Even if you have them memorized, please write them down. This is called equation of a line, slope-intercept form. Sometimes John calls it intercept slope. I don't know why. I prefer to call it slope-intercept because there's the slope and there's the intercept. Sweet. Okay, so in our problem, we've got 2 pairs of points. It doesn't matter which one you call the 1s. It doesn't matter which one you call the 2s, but you absolutely have to get both guys in the same parentheses with the same subscript so that we can make this work. In this example, it's going to be, let's see, and the other thing we always want to do is set this up with buckets so that the minus signs don't make us crazy. Because there are minus signs in the equation, there are minus signs in the points. Ooh, it can get bad real fast. So use buckets to keep everything neat and clean. All right, y2 is -3. See, there we go, drama right away. y1 is 2. x2 is 4. x1 is minus 3. So when we simplify, we'll get minus 5 over 7. Okay, so what that tells us is that the slope of our line is minus 5 over 7, and we're halfway there. Now we have to find, this is to find m. Okay, that's what we did here. Now to find B, the y-intercept, here's what we do. We take this and we plug in one of our pairs of points. And we plug in our value for m. And then we'll solve it for B. It's gonna be so fun, okay? I'm just gonna choose the first pair of points. It doesn't matter, either one will work. I try to choose the one with the cuter numbers. All right, so we have, it's y equals mx plus b. I know I'm writing it again. Let's put buckets in for everything except the b, because we know we don't have that. I picked the first pair of points, so y is 2, x is minus 3, and m is minus 5 over 7. Oh, that's dramatic, isn't it? But it's okay. This isn't going to hurt us at all. All right, we plugged it in. We've got one variable. We're good to go. Let's multiply this together. This becomes positive 15 over 7, right? I'm going to write that there. 15 over 7. So I'm going to subtract 15 over 7 from both sides. And I have to change this 2 so it's got a matching denominator. That'll be 14 over 7, positive. So it looks like that cancels. And I'm going to put my b over here. B equals negative 1 over 7. So now I've got my b and I've got my m, so I can write the equation of the line that connects those 2 points is y equals minus 5 over 7x minus 1 over 7. I bet that's really hard for you to read. Sorry, I had to squinch it. That's sad. All right, but that's our final answer. Yay! What that tells us is that this is a line. These are 2 of the points along here, but we can plug in any value for x, any value for y, and if it's a point on this line, it'll work. It'll be true, okay? All right, so that's how we can find the equation of a line when we're given 2 points. That's one style of point. Here's another one. This is example 10.2. Find the equation of a line that passes through the point negative 2, 5, and is perpendicular to the line 3y plus 4x equals 2. Okay, they didn't give us 2 points this time. They gave us 1 point and another line that crosses ours at a 90-degree angle. What do we do with that? Perpendicular lines have slopes that are perpendicular lines have slopes that are negative reciprocals of each other. So if we can find the slope of this line, then we can easily find the slope of our own line. So let's write it again. 3y plus 4x equals 2. We need to get it in slope-intercept format, so let's subtract the 4x Let's get the y by itself. We'll divide away the 3. And we get y equals minus 4 over 3x plus 2/3. Our line, this is the other line, if you will. I put air quotes on that. So our slope, or m, equals positive 3 over 4. Huh, good to know, right? That's so easy. Now, that's step 1. Just like before, it was find m, but we just have a completely different strategy because we were given different information. And then just remind you of this rule. Parallel lines have the same slope. So if we would have been told that these lines were parallel, it would have been even easier. Okay, so there's the first step, and then let's do over here, let's do step 2, find b. This is exactly the same as last time. We have a point. This time we only have one to choose from. So we'll go y equals mx plus b, and then we'll bucket the heck out of it, except for the b. Y is 5. X is minus 2. I'll put that in over there. And then our slope is 3 over 4. Okay, I multiply this together. I get minus 6 over 4. That's kind of crowded and messy. So I'm going to add 6 over 4. I'm going to add 6 over 4. I'm going to change that 5 to something with a 4 in the denominator, so that's going to be 20 over 4. And when I add them together, it's going to be 26 over 4. That all cancels, equals b. I can reduce that. I can divide top and bottom by 2. It's 13 over 2. So my final answer is y equals 3/4 x, because that's our m, plus 13 over 2. That's the equation of the line that meets those conditions. Holla. Did I say that out loud? I think I did. Okay, ready? Next topic. Whoop, there's 3 topics, you guys. I'm really sorry. This is a grinder. Example, in this one, our topic is rational denominators. Those words might not trigger anything for you, but when you look at the problem, you're gonna go, oh, that's right. 4 plus the square root of 3 divided by 2 minus 3 square root of 3. This is example 10.4. As a mathematician, when you look at this, I know what happens. Your hands tense up, you dig your nails into your palms, you feel the sweat starting to break out on the back of your neck, and you feel a flush creep over your face because you're so disturbed by this, because there is a rational number, an irrational number, a root in your denominator, and it can't be there. We don't want radicals in our denominators. We have to get rid of them. Now, if this was just this, we could multiply by square root of 3, and then the pigs would jump out, and they'd multiply with him, and it would be 9, and everything would be happy. But guess what? It's a binomial with a radical in it. Ah, good Lord, what in the world? So what we have to do is we have to multiply by the conjugate. I'm going to put parentheses around these two so I don't lose their binomialness. And the conjugate is this same pair of numbers with the opposite sign. This is a minus, so I use a plus. If this was a plus, I would have used a minus. If I multiply the bottom by that, I have to do the same to the top. Cool? All right, that's good. Now I just have to do the actual multiplications, and that requires going to the dance. So what I'm going to do first, I always do the bottom first, because magical things should happen there, and I want to check and make sure I set it up right so the magic actually happens. So I'm multiplying the two denominators as one does in multiplication. I'll multiply these first, and then I'll go over and multiply the tops if all is well. Okay, so there we are. These are the conjugates. That's what I'm testing. I want to make sure the conjugates work properly. 2 times 2 is 4. 2 times that whole thing is that. Now she's done. She's danced with both boys. Sit down. You had your turn. Now it's her turn. She goes over here, and it's, look, this is where the magic happens. That's what I wanted to see. And then I get minus, multiply the wolves, and multiply the pigs. Okay? Wait, I didn't do that right. Wolf to wolf, pig to pig. This, however, is 2 pairs of pigs, right? It's 3 times 3. So I can jump out one of the 3's, and this becomes minus 27. Make sense? I can do it over here if I'm thinking clearly. I can say, okay, these guys become a third 3. 1, 2, 3 times 3. No, not 3 times 3, 3 cubed. Does that make sense? Wherever if you want to write it down unsimplified and then take it one more step, that's fine. So now, I've got 4 minus 27, which is minus 23. Right, I'm combining these two because this all cancels away to a beautiful 0. And that's the magic of conjugates. It will always happen that way if you handle your math right and write it down properly. So that's why I always do that first, because I want to make sure that melted away so nicely. Now I can do the tops. 4 plus the square root of 3 times 2. And remember, this is driven by this, which is driven by this. So the top is usually messier. 2 times 4 is 8, plus 2 square root of 3. Then this becomes 12 square root of 3. And now let's see if we can do this one in our heads. We're multiplying these two together. These 3 pigs go together, jump out as 1 wolf, and then multiply by that 3, so that would be 9. So I'm going to put a plus 9 there, right? These two to go together, they make 2 on the inside is 1 on the outside. There's already a wolf of 3, so it's 3 times 3, that's 9. Okay, so I get 17 plus 14 square root of 3. Remember, if the radicals match, we can add them. It's just like having an x or a y. As long as they match, we can happily add away. Now I'm ready to write my final answer. It's 17 plus 14 square root of 3 over minus 23. That looks weird, doesn't it? It's right, but we don't always keep the minus sign down there. So what I want to do is I want to bring it out there. I want to erase it. I'd rather have the minus signs on top. So I'm going to multiply top and bottom like that and put parentheses around this. This is what I do when I want to move that minus sign somewhere else. Now it becomes minus 17 minus 14 square root of 3 over a positive 23. Both of these are equally correct, but my mathematician's brain kind of smiles on that one. John chose both, just so you know. And both are correct. This just feels a little neater and cleaner. Okay. One more problem in this section. I know, there's one more after this. Buckle down, you guys. Okay, ready? Simplify. Two minus I cubed plus 2i to the 5th over, oh, not radicals this time, but complex numbers. Okay, well, let's see what we can do with this. The first thing I notice is that this could be cleaned up, because remember, every pair of i's equals a -1. All right, so and then let's regroup. We always want our complex numbers. We want to have this form. We want to arrange them thusly, right? This doesn't look good. This looks yucky. Okay, so let's go through and clean this up. This is going to become, we can take 2 i's away from this. That will make a negative. That will make this positive. And then we'll just have 1 left there. And then this will take 2 negative 1's, right? Because it's I to the 5th, so I squared is -1, I squared is -1, plus there's 1 left. These two go together to make plus. That stays the same. So we will have 2 plus 3i when we clean that up in the numerator. All right? And then the bottom is simplified, but I don't like the order. So we're going to change it. All right. I'm feeling better about this. Now, we have the same thing down here. We typically want to have a rational denominator rather than imaginary numbers. So we use the very same technique as before, the conjugate. 4 plus 2i. Same terms, change the sign. Top and bottom have to be the same. Okay? Again, let's do the bottom first to make sure that the conjugate did its job. 4 minus 2i, 4 plus 2i. 4 times 4 is 16, minus 8i. Here comes the beauty. Okay, now let's go carefully on this last multiplication. It's going to be, it looks like it's going to be negative, but let's do the other parts first. It's 4. Then these two go together to make an I squared, which carries a negative to the product, but we already have 1 negative, so it becomes a positive. This cancels, and so our new denominator is 20. Oh, I like that one, don't you? It's way better than that 13 we got the other time. Or what was it, a 17? 23? Ugh, not cute. Okay. Good, I feel good about that. Our conjugate did its job. It looks really good. Now we'll try this messier one. 2 plus 3i times 4 plus 2i. This is not going to cancel out all cute and sweet because it's not a proper conjugate, but that's okay. We can handle a mess upstairs. 2 times 4 is 8. Plus 12i plus 4i plus, okay, here we go. 2 times 3 is 6. I squared is -1, so that changes the plus into a minus. So when we combine this, 8 minus 6 is 2 plus 16i. All right. 2 plus 16i over 20. And that's correct, but I notice, oh, all of these are even numbers. Can we do some canceling? Yes, but technically we have to factor first. We can't cancel when we're adding. We can only cancel when we're multiplying. So what we want to do is factor the 2 out of this, leaving us with 1 plus 8i, right? We pull the 2 out. 20 stays the same. Now we can cancel because this 2 is being multiplied and not added. And so this becomes a 1. We'll just not write anything. This becomes a 10. And we're going to write it one more time, and we're going to remember this is the format we like for a complex number. So it's going to be 1 over 10 plus 8 over 10, but we can change that to 4 over 5i. That looks cute. I'm pleased. So that's the trick we use to get rational denominators, because we factored out, or we eliminated the irrational radical sign, and we eliminated the irrational imaginary number. Okay, so we rationalized both of those denominators. That's what those problems had in common. And in both cases, we used the lovely conjugate technique to wipe out the bad boy. All right, last section, completing the square. Oh, you guys, I just love completing the square. What does that make me? I don't know, but I love it. Okay, this is the way we solve a quadratic equation to find out what, it's usually x equals. Let's just dive in and I'll explain it as we go. 10.6, we only have one of these. This is the last problem. All right, ready? It says solve, and then it gives us this hooliganism. This is one unruly problem. All right, well, I mean, we're supposed to solve it by completing the square. John tells us what to do. He's bossy like that. This is a hot mess. The first thing we want to do is put this pup in standard form. Oh, what is standard form, you might ask? Okay, well, that's where we have an x squared term plus an x term plus a plane number, and it's all set equal to 0. Okay, so we want this to look like that. And it's not going to be that hard. This just needs to go first, 3x squared, and then the minus x can go next, and then we need to move this over so it'll change his sign, so it'll be plus 5 equals 0. Okay, cool. So we cleaned it up and we put it in order. Sometimes John's nice and he gives it to us all pretty. This was not one of those times. 2, kick C to the curb. Now, I say it this way specifically. I don't tell you to move him to the other side. I tell you to kick him to the curb. That's going to make sense to you later this year. You'll understand why I said that. But for now, just think of it as we're kicking him to the curb. We're going to move him back over there, change his sign, and I'm leaving a gap there. That gap I'm leaving on purpose. Let me write that, leave a gap. Because that reminds me of what the next step is. I need to put something in there. What goes in there? Oh yeah, the magic number. We're going to put a magic number in here that's going to turn this side of the equation into a perfect square that will be really easy to simplify. How do we figure out what this magic number is? We take the b term, the numeric coefficient that's on the front of the x, right? Right there's the b. It includes the sign, so let me put that there. We take the b term, we divide it by 2, and then we square it. That's how we find the magic number. I always write it like this and draw an arrow because this number inside of here is going to be very helpful to us in a future step. So I always put that arrow there. Now we can put ours in. Our value for b is -1. So it's -1 over 2 squared. Again, I do this. -1 over 2 squared equals 1/4, right? So I'm going to add 1/4 here. I add my magic number. And algebra being what it is, we have to add over here as well, right? Okay, this has become, oh, I did something wrong way back at the beginning, you guys. I forgot to divide away our 3 coefficient, and that changes everything. Stop the presses. Let's start over. Okay, I'm just going to leave all that. I'm not going to erase. Okay, standard form. That was okay. 3x squared minus x plus 5 equals 0. Then, divide away the a, right? That's the coefficient on the x squared. So we have to divide every term by 3. This always bothered me, but it's fine. And now what we have is x squared minus 1/3 x plus 5/3 equals 0. Okay, that always bothered me that it doesn't really change the other side, but it's fine. Trust me. Now we kick c to the curb. And we have x squared minus 1/3 x with a gap and then it's minus 5/3. Now it's the magic number. Whoops. And this isn't wrong, but the way I calculate it is to say it's B is minus 1/3 times 1/2 quantity squared. Better? Oh, that's so much better. So now this becomes minus 1/6 squared, which is 1/36. And I draw my arrow to that. Okay, so now I add 1/36, that's my magic number, plus 1/36. Have to do it to both sides to keep it in balance. Okay, now I have a perfect square. And this is going to be x, and it's the number in here that goes right here. Minus 1/6. So that's why I always draw the arrow to my magic number calculation, is because that's what's going to go here. I can test that just to be sure, because remember, these two multiply to become this C term, and they add to become this term. If I multiply these two, I get positive 1/36, and if I add them, I get negative 2/6, which reduces to negative 1/3. So what I'm saying is, if you multiply these two, you should get that, and if you add these two, you should get that, and that's how you can prove that this is correct and you're still on track. All right. Are your eyes bleeding yet? They might be. Now I can fix the other side of this. I have to add negative 5/3 to this. I better multiply this by 12/12, right? So it matches. So this is going to be negative 60/36, right? 5 times 12 is 60. 3 times 12 is 36. That's gone, and I'm adding them. So that becomes negative 59/36. Huh. Intense, right? These numbers are getting kind of nutty, but we're almost done. This now we can restate. X minus 1/6 squared equals negative 59/36. And now, rather than turn the page, I'm going to reclaim this space and take this on up here. That's not confusing at all, is it? What I need to do to get rid of that square is I need to take the square root of both sides. So now I'm going to say x minus 1/6, which is this, equals, ooh, I'll write it the long way. I won't take any shortcuts here. That, plus or minus, because in algebra we have to consider negative roots. If this was a geometry problem, we could rule that out, but we have to consider the negative root, so that's plus or minus, hard to read. Now I want to simplify this. I'm going to consider them separately because the bottom's cute, and it will always work out this way. The bottom simplifies. Square root of 36 is 6. 59 is prime, and it's negative inside of a square root, so I need to rewrite that as square root of 59i, right? We're almost there, you guys. Now all I need to do is add the 1/6, because I'm trying to get this x by itself. So I want to add 1/6 to both sides, and I get x equals 1/6 plus or minus the square root of 59/6i. This is the cleanest presentation, is to let that I float in front of that fraction. That was a whopper of a problem, you guys. That was a whopper. And it didn't help that I forgot to get rid of my 3 coefficient up there. So sorry. But you can see mistakes happen. It's okay. And you don't have to erase every shred of evidence from the face of the earth. Just leave it, it's fine, right? You can still see my notes. You'll remember this, right? Because you'll go, oh yeah, remember the time my teacher screwed up and forgot to do that? And you'll remember, and it'll be great, great fun. Okay, that is the end of lesson 10. That was long, that was thorough, that was full of algebra, and that was kind of fun, don't you think? I enjoyed it myself quite thoroughly. All right, that's the end of lesson 10. Good luck with your homework. Remember, the homework is the hard part, right? Doing the lesson with me, that's the easy part, because watching me do it is way more easy than doing it yourself. The homework is where you really get your learning done. So, good luck. Kill them. Go destroy those little math problems and show John what you're made of. Okay, thanks you guys. Bye.